this التوك دلوقتي لغايه ما الجماعه لو اي حد اجنبي يجي يتكلم بالعربي دي فيها حاجات كتير جدا. فيها انا ما كنتش ناوي اديها بالمنظر ده بس قلت عشان تسمرايز مثلا احنا ادينا كوزمولوجي في الاسبوع الاولاني ونكسي اتكلم شويه عن البرتربيشن. عايزين نعرف ازاي تمشي من الهوموجينيوس ايزوتروبيك يونيفرس ده وتعمل حاجات بجد زي جالاكسيز وبعد كده نجوم وبتاع. عايزين نشوف الاوبزرفيشن الحاجات اللي احنا شايفينها. طبعا مش هقدر اقول ده باي تفصيل خالص او بس هنكمل الموضوع ان نرمي عليك حاجات بس بقى ايه ده اللي بيسموه في المزيكا الكريسندو ده الفينال بتاعها. لا هيترمي حاجات كتير قوي يعني بسرعه. So there'll be really a lot of stuff يعني من الاوبجكت هو ان ندي فكره عن ايه الحاجات اللي نقدر نعرفها عن اليونيفرس اللي احنا شايفينه بجد جالاكسيز وستارز وكده وايه الحاجات اللي ناقصه. وهنلاقي ان اللي ناقص كتير جدا بس اللي عارفينه quite remarkable يعني. ندي فكره عن الاثنين وناخد فيدباك عن what do you think على ده وعلى in general يعني what you heard في الاسبوعين اللي فاتوا او الاسبوع اللي قبل العيد والاسبوع ده and what does it all does it يعني ايه الحاجات الجديده اللي فهمتوها. ان مثلا كان بيتقال كتير ان من الناس اللي مقدمه ان احنا ما نسمعش عن الحاجات دي خالص وعايزين نسمع عنها اكتر كده. I think you got your من الناحيه دي يعني خدتوا فلوسكم. المشكله ده يمكن كتير قوي متبعتره جدا. No, that's normal. ان الفكره من كل ده ان it's a matter of بالذات التوك دي it's window shopping اكتر ما يكون يعني ايه window shopping بتتفرج على المكانين وتشوف هتشتري ده ينفعك ده ما ينفعش عن ان انت فعلا يعني تنقي الحاجات بجد وتعرف المواضيع بالتفصيل. ان ده impossible يعني المحاضره دي لوحدها مثلا it would take مفروض على الاقل محاضرتين مفروض 3 4 عشان تبقى السن واضحه بالثلاثه اللي فاتوا اللي غالبا انتوا نسيتوهم قبل العيد. يعني دي كده المفروض تبقى 3 4 محاضرات ساعه وربع كل واحده مثلا. اوكي فدونت بي سكيرد. الفكره ان انت you can take a general overview and idea what's going on. دي وقف يا محمود فين محمود؟ اوكي what do you mean by a perturbed universe؟ يعني الايزوتروبيك homogeneous universe ده طبعا اللي احنا كنا بنتكلم عنه ما ينفعش. need to show الماب دي مثلا بتاع الجالاكسيز. عايزين الخريطه دي نطلعها. عايزين نطلعها ايه؟ عايزين نطلعها من الكوزموس مايكرويف ده اللي بنتكلم عنه هنكسيه ونتكلم عنه شويه بسرعه في الدقيقتين 3 اللي بسمح لنا عنه او 5 دقايق. الهدف ان عايزين نطلع من الانفليشن دي بتاعت الكوانتم فلكتويشنز واللي بتتمط on the classical scale وبتاع وبعدين perturbations اللي بتعملها في المترك. عايزين نطلع من ده ونعمل جالاكسيز بتنور ونعدهم ونعمل ماب زي دي كده للجالاكسيز ونطلع الباور سبيكترم بتاعها. يعني ايه باور سبيكترم بتاعها؟ نمسك الدنسيتي دي هنا وناخد الافريج بتاعها اللي هو الهوموجينيوس ايزوتروبيك وبعدين نطرح منه اللوكال دنسيتيز اللي هي اهو الاوفر دنسيتي والاندر دنسيتي ونقسمها تاني على الافريج فبناخد الدلتا رو اوفر رو الريلاتيف دنسيتي كونتراست وبنعمل له فوريه ترانسفورم. You probably heard ان الفوريه ترانسفورم ده مهم جدا في حاجات كتير قوي من اول الانيليشن كريتور اوبريتورز لغايه الدنسيتي ماب بتاعت الجالاكسيز. اوكي تاخد الفوريه ترانسفورم بتاعت البتاعه دي بتربعه ده اسمه باور سبيكترم. you're here. Okay, I'll switch things because I thought you and Alexei weren't here or Nico. Okay, so you take the density contrast here and you take the Fourier transform, which, as I was saying, was important all the way from creation to annihilation operator to the density map of the universe. It's a very generic thing that you should know very well. You take the Fourier transform and you take the square on the Fourier transform, and you call it the power spectrum. You want to understand that. For example, I want to understand the power spectrum of this also, which is the fireball on the cosmic background. Okay? So, a really important thing about gravity is, as we said in the very first lecture, the first 5 minutes, it's long range and it's attractive. Which means it keeps on clustering and there's nothing to prevent it. If there's no force to prevent gravity from clustering, it will eventually make black holes in the end. Okay? If not, at least it will make clustered things, not homogeneous media. Electrostatic forces are also long range, 1 over r potential, not e to the minus. It's also a long range thing. But they are positive and negative. So there's something called the Debye length in a plasma where they equate and so on. But this doesn't have a Debye length, but it has what's something called the Jeans length. So if you have a sound wave, what's a sound wave? A sound wave is a compression and rarefication of a gas. Compression and rarefication. Compression and rarefication. I compress the gas, it rarefies and so on. A normal sound wave goes like this. Here's your speaker, here's over density, under density, over density, under density, and I hear it as a sound wave. In gravity, if the wavelength is very big, the self-gravity becomes very big. So, no matter what the pressure or forces you have that bring it back, maybe ohms. You compress it, maybe ohms. So this is called a Jeans length, where you start clustering. So instead of having a normal wave like that, your wave starts, as you increase the wavelength, the amplitude becomes larger, larger, until it forms something. Okay? So this is the basic mechanism where very small perturbations, if you don't have enough pressure, will always form you something. And this is the basic mechanism from which everything forms from a nearly universal thing. More formally, you can do it with hydrodynamic equations. This simply says that mass is conserved. This is a conservation equation. So any change in density in time is equal to the mass flux in a small box, is equal to the flux. So that's all it says. Change in density in a small box is equal to the mass flux, rho times velocity. And this is a momentum conservation equation. It's Newton's law with a Lagrangian derivative following the motion, total derivative. So this is like dv by dt, x double dot, Newton's. And this is a pressure force, it's called a pressure force, and this is a gravitational force, obeying Poisson's equation in the Newtonian limit. Okay? So these are the equations that describe my waves. How do they describe my waves? You already another thing that you had a lot these days, linearization of equations. So you make a small perturbation to your density and your pressure in these hydrodynamic equations, and you neglect higher order terms, delta rho squared and delta rho delta p and things like that. You neglect these terms. What you get with that gravity is a sound wave. And again, the Fourier transform, which is something you really need to know clearly. And so if you take these equations, the continuity and Euler equations, Newton's law and mass conservation, momentum conservation and mass conservation, and you linearize your equation to first order, you get a wave equation with something called adiabatic sound speed, which is volume compression, basically. The compression of the response of the pressure to volume compression with a change in density. The relation between them is the sound speed squared, okay? Without dissipation, meaning no energy loss due to heat. So this gives you waves that propagate infinitely with the speed of sound. So you get these equations for Fourier transform in space and time, you get omega and t frequencies. And they oscillate because this is I, which is sine and cosine, That's what stuff was saying. So therefore, these are sine waves. Okay, sinusoidal waves, and you get this standard, what's called the standard dispersion relation between the wave numbers, 2 pi over lambda, 2 pi over wavelength, and the angular frequency. Okay, but with gravity, you get the extra term from the Poisson equation, and this can be, the frequency squared can be negative, which means instead of sinusoidal, you can get exponential blowing out solution. This is not an expanding universe, this is like in the lab, well, a very big lab, okay? Or star formations like that also to first order. This is not yet for galaxies, this is just general. When they are equal to each other, you call this a Jeans length, okay? A Jeans length is when the gravity wins. When the wavelength of the wave is so long that self-gravity is important enough to cancel out the sound. Also, you heard a lot about causality. This is, you can see it as a sound causality. Is the sound wave propagation faster or the collapse time faster? The collapse time faster, then the causality of the sound, so to speak, then you collapse. If not, you don't. Okay? And so this is the criteria. And this is how we get from this state to this state. Okay, to caricaturish approximation. And this state is characterized by this thing, which sometimes is called the Virule Equilibrium. So in Schumann's language, gravitational systems are always near a critical state, potential energy near a kinetic energy. And they can also, the Newtonian potential and the Newtonian limit, it's a power law, so you can always rescale your system in terms of a dynamical time. So a galaxy with the same density as a little ball will fall in the same time exactly if they have the same density. It doesn't matter what the length scale or the length scale is, or actually the mass scale. What matters is m over r cubed, not r and m. And you can do this very simply from rescaling the Newtonian equation. All solutions can be rescaled like that. So this is a sort of universality, okay? But it's even, I mean, this is something that even numerical simulations, if you do a numerical simulation in a paper and you want to do another one, rescale it to a cluster instead of a galaxy, you don't need to do the simulation again, as long as there's only gravity, no hydrodynamics and so on. Then, things like that. Okay? So you can think, is this how really galaxies form then? No, they don't form by the I mean, you can imagine adiabatic cooling of gas that with the universe expanding, and then you form galaxies from simple gas from Jeans instability. No, you don't. Not like that, because of the CMB tells us that the universe was too hot, and the baryons meaning generally anything ignorable matter in astrophysics, were coupled to these photons until the recombination time, which Alexei mentioned briefly. So what is the CMB? This is the cosmic microwave background. It's the most pure Planck spectrum you can always ever get. You can't get it in the lab. You can't get Planck spectrum like that. So it tells you there was some good approximation an equilibrium state with a nearly perfect Planck spectrum, from which you can tell the temperature, because it's parameterized by temperature. It's a maximum entropy state parameterized by temperature. So the temperature nowadays is 2-point-something Kelvin, 2.73 Kelvin, which is 10 to the minus 4 eV. This is the temperature of the cosmic microwave background. And this is the energy density. You can calculate also the energy density by simply measuring the energy density of the cosmic microwave background once you detect it. And this is detected very long time ago, 67, 68, something like that, sometimes also. And you'll find it to be 2.6 times 10 to the 5 eV per meter squared. This is a joule here. You'll find if you divide this by this, and because of the Planck distribution law, a photon has an average energy h nu that is roughly equal to kT, the peak here. So you divide the two by each other and you'll find that you have like something like 10 to the 9 photons, CMB photons per meter cube. So that's a lot. In this room, there's then 10 to the 12 or whatever photon CMB going around. So, but their energy is very small because they finally but there are many more than the baryons. In the universe, there's only one proton per meter cube on average. There are many more in the room, but in the universe as a whole, it's much more empty. But there are more. There are many more CMB photons, and from this you can tell when. If you remember, something we mentioned a lot is that the radiation energy density goes 1 over a to the 4 scale factor with the constant, and matter 1 over a cubed. From these parameters here, you can know when they were equal, because the radiation goes بتضرب a to the 4. زمان كانت أقوى, before it was much stronger, and now we are matter dominated. And it turns out to be a redshift of a couple of thousand or something like that. A little bit, half the redshift of half the scale factor of the recombination time. The recombination is you get it, like Alexei was mentioning, also from 13.1 eV, which is the hydrogen, which is the dominant element, hydrogen ionization time. Ionization energy, but it's much less. It's about an order of magnitude less than that because there are 10 to the 9. Very crude estimate is divided by log 10 to 9. So you get a fraction of an EV. A very crude estimate is that. So this is when the CMB photon left the scattering, they're coupled by scattering to electrons, Thomson scattering. And after that, they're not coupled because hydrogen recombines, becomes atoms, and the CMB comes to us more or less like last scattering surface. أو emitted from the last scattering surface. So, and this is a graphic picture of how it looks like. There are fluctuations in this. So you get your telescope, your CMB telescope, microwave telescope, WMAP or Planck or things like that, or sometimes ground-based telescopes like that, and balloons and things. There's lots of experiments. There was a balloon. What was it called? It had this strange Australian name. Anyway, there's many ways of measuring the microwave background. You point your telescope to different angles in the sky, and you measure the average, and you subtract from the local, like we did before, and you can always do a Fourier transform, like we did with the power spectrum, and you find that to a first approximation, it can obey a wave equation of a photon fluid. Okay, there is an appendix in these slides where it shows how you can get this thing, also not very precisely, but a sketch of how you can get this equation for a photon fluid. Why do you get a wave equation of a photon fluid? Because it obeys continuity equation, okay, and it obeys, and it has pressure, so you can do an Euler equation for it too. It's a pressure third of the energy. Why does it have pressure? Because it has momentum. As we showed with the energy momentum tensor, pressure is averages over the momentum, over the isotropic part of the matrix. Okay? So there are these appear to be propagating waves, which you can Fourier transform, but a complementary and more used technique is a Fourier transform in polar coordinates, basically, which is circular harmonics expansion. So this tells you, this divides this power, this is a power spectrum in angles instead of a power spectrum translation invariant. This is a rotation invariant for circle symmetry will be constant. Okay? So this basically tells you, divides your fluctuation, this fireball, this color-coded fireball that I showed, tells you what are the different scales. The fluctuation power, the Fourier transform tells you the power at different spatial scales. This tells you at different angles. Okay? So you can, and also you see it frozen at B combination, at the last Kaplan surface. So all the same, which is determined by a sound horizon. A sound horizon is the time the sound took to travel from very small times, from the beginning of expansion to the time of recombination that you are seeing the snapshot. So this is your sound horizon. And then your solution will be a cosine function. This assumes the adiabatic initial conditions so that there are no theta dots here. That's a detail. Okay, so, and this is your wave number, different wave numbers, many different modes. Fourier modes are propagating, and this is your sound, the distance, which you get. Since the speed of sound in a photon fluid is the c squared is a third of the speed of light squared, because of basically comes from here. Okay, so times the conformal time, which we studied before. I use physical units to make things, I don't know if it's simple or not, but to make things explicit, of course we wouldn't have that, but I'm using physical units. Okay. Right. So then you will find peaks at compression, rarefication, first compression, first rarefication of the sound wave, and so on. And then there is damping. Why is there damping? It's like if you are the وقت الساحل and you hear a party long, far away, you'll think there's no treble, there's only bass. كله boom, boom, boom. فين السكسكة؟ ما فيش سكسكة عشان السكسكة is damped because it's short wavelength. And first of all, it has undergone many oscillations. And second, because it's a small wavelength, so there's diffusion out of the waves. So our approximation of no dissipation and so on doesn't become very nice. So this is called the damping tail. This is where they get the power spectrum from because it didn't yet oscillate at all. Yes, neutrino and baryons also. Yes. Yeah. So this is where the damping tail comes from. Yes. So then if you look at the first peak, the co-moving length of the first peak is just that, the sound horizon. Okay. And we have an angle. When we did the spherical harmonic thing, we can go the power at different angles. So عندنا عصاية, an angular distance, المقاولين. Okay. We have عصاية بعيدة جدا. We have a ruler that we think we know the size of. So we have an angle and we have a ruler. So we can know the distance. Okay, so you get it if the peak is like at 1 degree and it's like 0.017 radians, and if you do the calculations of the first peak, we're a matter-dominated universe, because most of the time since then, well, all the time, but significantly after the emission was really matter-dominated. So it's a good approximation, and also only very recently has there been any dark energy importance. So for most of the time, you can assume that you are a matter-dominated universe where the scale factor scales like that, very simply, like we did in the first week. If you don't, go look at it, and then you cube this, and you find that if for 14 gigayears nowadays, this thing is like 300,000-400,000 years. Just by looking at this and very simple calculation of a photon fluid, you can get more or less the right numbers, right? The distance to the CMB. Or if instead you know the redshift and you don't know the angle, you can get the angle. And this tells you what? This assumes the simple calculation assumes a flat curvature universe. So it tells you that flat curvature is a good approximation, at least to this really low-level order. Yeah? At this crude level. And it tells you another thing, that things here are really beyond the sound horizon, which means they couldn't really have communicated even light, because it's only square root of 3 difference. So you need things that they could have communicated, they were close together and then inflated. Because during this time, from the beginning of the expansion to 400,000 years, there's no time in a normal radiation-dominated universe or for normal sound speeds to either in radiation or matter dominated for the sound horizon to be large enough. It's only 1 degree or something, and you have all the way to 90 degrees here. So why are these things communicating? They appear to be similar to each other, in the sense of having the same power spectrum and so on. Okay, so you can always know the curvature like that because it's like a bit like, very roughly speaking, an analogy is like lenses, concave and convex lenses. Things appear closer in a curved universe that is positively curved and further away if the light rays are divergent. Because simply this is longer than this. Okay, so things look bigger. Okay? If you are naive and assuming you're purely Euclidean and it's not, then things will look bigger. But the flat, so you can measure the curvature of the universe from this rod, okay, there. Okay? And you can measure the baryons because we assume the photon fluid, but you can have baryons also. So, and baryons don't contribute to the pressure because they're not fast moving enough relative to the photons, which are moving in the speed of light. So they change the sound speed when you put them together here. They have a different expansion, different energy density change, and they don't contribute to the upper term by the rapid sound speed. Okay? And they change the sound speed and they change the amplitude. Because you have a component that contributes to sound gravity but doesn't contribute to the pressure. So it changes the amplitude of the oscillation. So from there, from the second peak particularly relative to the first peak, you can know something about how much baryons there are. The dark matter, because it doesn't participate at all, it's not coupled. If it exists, if it's not coupled to the oscillations at all, it damps it because it doesn't participate at all in these oscillations. Okay, the details are a bit more complicated, but you want to have a discussion, not like a detailed thing. Okay, so the most important thing for all of that is that you can measure the parameters of the universe. Take home, this is the take home thing, from the CMB. And you'll find more or less the same that we found in the first week, if you remember, that it was 70% dark energy, 25% dark matter. You can't find this from late universe observation, but you can find that this total 25%, 30% baryons plus dark matter. Okay? That's what you find. You don't really find from the late universe observation that. You find it from here, and you find it from something else called Big Bang nucleosynthesis, which I think you mentioned, did you? You mentioned briefly Big Bang nucleosynthesis. Well, anyway. Right. Okay, dark energy also changes the power spectrum because it changes the distance to the CMB, and so you can distinguish between different models, lambda, cosmological constant, and other dark energy and so on, from the CMB data like that. Okay? So you can measure, and you can measure in the end the Hubble constant for reasons that you may look at the notes on the free lectures in the first week. The Hubble constant enters into the angular diameter distance and so on. So you can measure that as a parameter also, and you get this value, which is disputed. Okay, so what else? So, okay, we have the CMB. One of the important things, because of this damping, the primordial fluctuations are damped in the baryons. So they cannot form really galaxies from baryons, from baryon fluctuations. If you have inflation and you have your quantum fluctuation, you perturb the metric and you do your density perturbations on, they will damp because of the diffusion damping in baryons and photon fluid and neutrinos and everything. Right? So it's the smallest scale you can do our genes instability is that of a galaxy cluster or more, or which were called Zeldovich pancakes a long time ago. Okay, which are a scale of a galaxy cluster. You can do galaxies in time also. Okay, so how do we do galaxies? So this tells, the CMB also tells us that we can't do galaxies with GR. I mean, you can always boost it with something else, but with GR, you cannot do galaxies, and you need, the spectrum needs dark matter, that's one thing, and second, tells you that you cannot form galaxies and things with baryons alone. You need dark matter. So the CMB, in my opinion, I think most people working in the field, is far stronger evidence for dark matter than the rotation curves. The rotation curves are evidence for MOND. And that's an opinion that many people have. This is not a very controversial opinion. It's likely, but not very. Rotation curves, galaxy clusters are intermediate. But rotation curves are evidence for modified gravity. CMB is evidence, strong evidence for dark matter.
What about the crystal lensing?
It's intermediate also. You can always fit it, but difficult to fit with the modified gravity. That's my opinion. The gravitational lensing, you can fit it. It's intermediate. But yes, there is good evidence. That's good evidence also for dark matter. Yeah. Because if you fit it, if you make models of the weak lensing structure in the universe, and you do your standard halos, that will come to the halos now, and put them there, it fits quite well. It's a standard model, the lambda CDM fits quite well, the gravitational. You can always tweak the modified gravity. It's not distinguishable enough, but the standard model fits well with the lens. Doesn't have any problem as far as I know. Okay. So the dark matter is great because it doesn't have any pressure. Before we get to the pressure, that's why dark matter can't be made of neutrinos, of standard neutrinos like the ones Mustafa was talking about. Because the standard neutrinos have very high speeds. Even if they have mass, they'll still have speeds close to the speed of light or thereabouts. They'll also form structure at cluster scales, at megaparsecs or more. I don't remember the exact number, it's a lot. It's big. You need structure at small scales. You need to form small galaxies that are over the kiloparsec range, okay? Not megaparsecs, okay? So 1,000 times smaller. So how do you do that? The standard thing is the CDM, which are massive, weakly interacting massive particle WIMPs, which we didn't do the Fermat history, but you can produce them very nicely theoretically, but probably doesn't work experimentally, but it's nicely. So the WIMPs are massive, so in thermal equilibrium they move very slowly. So the streaming length is also in the appendices here of the slide, so you can look dark matter streaming, you can distinguish between cold dark matter, hot dark matter, warm dark matter, blah, blah. Okay? So this is streaming length, this is the velocity in kinetic equilibrium, and the streaming length is related to that. It's related to something here that, so the dark matter doesn't have any pressure. It follows the density contrast, delta rho over rho, from our Euler equation. You can, it's derived also in the appendices because we want to try to save time. It follows this equation, which is very similar to the equation I showed you in the first slide, the wave equations with gravity, but without pressure now, so it's not really wave at all. It's direct collapse, but it's slowed down by the expansion. So for a matter-dominated universe, instead of your negative exponent, which is an exponential blowout, you get a power law. Okay. For radiation-dominated, the matter doesn't collapse because the expansion time is dominated by the radiation, which doesn't collapse because it's pressure. And the matter collapse time is dominated by the matter density, which is small. So 1 over g rho, square root g rho, the time scale of collapse, okay, of the matter is larger than the time scale of expansion, which is 1 over squared g rho, related to h minus 1, the Hubble time, the expansion time, due to the radiation, because rho radiation is much more than rho matter. So nothing collapses, okay? You can solve it for radiation and find that it collapses logarithmically, but that's a detail we won't get into, okay? This is called some Mésaros effect, okay? This is all in the Newtonian limit, of course, okay? So small compared to horizon, I'll discuss very briefly horizon, not really, actually. But this is in small scales, okay? You get corrections due to GR, but within the horizon, the causal they're usually not very important up to horizon scale, only a few percent. Not very important. So for practical purposes, which meaning finishing this lecture, I will assume it's Newtonian. Okay? Right, so this is the primordial power spectrum again. This is the primordial power spectrum of potential fluctuations, which Alexei talked about, which are metric fluctuations. Here, there are potential, taking one of them here. And it's nearly scale invariant in the sense that this means that it's the same in power, same fluctuation power on all octaves. From 1 to 10, similar 10 to 100, 100 to 1,000, 1,000 to 10,000, and so on a logarithmic scale. The variance is equal on equal logarithmic scales. That's what scale invariant here, constant. Meaning the power spectrum itself is proportional to the volume, as opposed to the white noise, which is like random noise, due to randomly distributed particle, which goes over, which is constant. And this thing goes 1 over the volume. So it's like a fractal. So it would tell you actually like that everything collapses at the same time, but that's not the matter power spectrum. That's a metric or potential power spectrum. The matter power spectrum is a bit different. I'll do it in the Newtonian limit with a Poisson equation, which is valid also in some coordinate system in GR called moving. You move with the fluctuation or the matter perturbation. Okay. So again, Fourier transform this thing. You put e to the power of IKR, e os to IKR. So you do a second derivative here, you get a k squared. Okay? Fourier transform again. E to the, you say phi k is equal, pi is equal to some a, or integral of phi k e to the power of IKR, and so on, and so same with the rho k, and so you get the k. You get a relationship between. That's why Fourier transform is important again, very powerful from everything from the harmonic oscillators and quantum mechanics, quantum engineering, to Poisson equation solutions, to observational things, to analyzing the CMB, to you should get it into your head. So you get that the matter, the dimensions matter power spectrum is not flat, it's k to the 4. Okay? So it increases like that. Then it flattens here due to the Mésaros effect. In this co-moving gauge, outside the horizon, the modes grow. Inside the horizon, the causal horizon, the modes don't grow during the radiation era because of the simple heuristic argument again. So دول بيتأخروا الموdes اللي هي small wavelength large k 2 pi over lambda, okay, 2 pi over lambda. دول بيتأخروا عن دول. So there's some flattening, and you can take a look at this little argument here to convince yourself. I'm not going to go into it, but you can convince yourself that this factor of k to the minus 4 and k to the 4, approximately, this is heuristic, that explains that this thing flattens, okay? Instead of k to the 4. Okay? You can take a look when you're done. So this thing is scale-free, because we didn't have a scale in this problem. That's another thing we've been talking about, scales and problems and stuff. There was a delta without a k when we took out the pressure. There was no Jeans length anymore. Everything could collapse. So it's scale-free. So in the linear regime, everything matter domination again. everything grows self-similarly. All scales grow in the same manner. But we have power on small scales that is larger. So the perturbations in density are increasing with time. They reach a threshold which is called top hat. You'll find it also in the extra material in the end if you want to do the top hat. احنا في تطبيقيه للجامعات الحكوميه هنا كان اسمها Cycloid Solution. سلك سايكلويد ما خدتوش سلك سايكلويد؟ نعم. سايكلويد ما خدوش عادي سلك سايكلويد. So anyway, this is called the Cycloid Solution. You expand and then you collapse. It's called top hat because it's like a jazz top hat. You expand and then you collapse roughly when this thing is equal to 1, when the dimensionless power spectrum is, when the perturbative limit, so to speak, is not valid. Okay, when your delta gets to 1. It's very near there. Actually, a little bit of work shows you it's 1.7 or something. 1.6 something. Okay? So, and the standard, and this is if you have a Gaussian random field. Okay, I won't get into that, but it's in the slides, and you can look at the references if you like. A Gaussian random field is random, and it has, when you decompose in Fourier mode, it has random phases. So the phases add up according to the central limit theorem, which says many numbers that are random adding up give you a bell curve or Gaussian distribution. So briefly speaking, that's what a Gaussian random field is. And you can get a probability from this thing. This is called the Preschector formalism, if you want to know that. Okay? You can get a sort of, you can see where the Gaussians are here, and you integrate over them and get error functions. You can also find it in the references. We're supposed to have a discussion. So, okay. So you form small things first. Small thing, because the power spectrum is tilted towards the large K small wavelength. So you form small galaxies, small halos first, dark matter. This is all in the dark matter, okay? Because you cannot form in the baryons, this thing actually is cut. This power spectrum in the baryons, because of the damping, the diffusion damping that you see in the 7B, there's no power. So you can't form these small galaxies. And if you only have baryons without dark matter, there's no small galaxy. You need to form them with dark matter. Okay? So small ones, bigger ones, clusters in the end. At z equals 0, nowadays, we are forming clusters. At the very beginning, we were forming small galaxies. And you can map the galaxy distribution and do the power spectrum. Again, you take the Fourier transform, density here, density contrast, delta rho over rho, and square it. And compare it with observation, you'll find that it fits very well. This is from observation, and this is from theory. It fits very well with the same parameters of 30% matter and a little bit of baryons and dark energy and so on. Okay, so you'll find this is very old, but there's much better stuff nowadays than this plot. Okay, so you can find that with the same parameters you get from the cosmic microwave background and the background evolution, you can fit the power spectrum of the galaxy distribution from this very simple model, which is on large scales very nice. On large scales, 10 megaparsecs and more, maybe even a megaparsec or more. It works very nicely, this thing. Why? عايزين نتكلمها بالبلدي. It's as if the baryons, the galaxies that we are measuring, follows the dark matter. If you have phosphoric little particles in a fluid moving, they will follow the fluid on large scales. But if you have little انسدادات طينة, you start having mud and so on, they wouldn't follow the fluid. No, this is very rough. Okay, so, but you can do simulations also that I showed you in the first week. So you start with the power spectrum you get from the very large scales on the CMB. This is called the Kobe normalization to the scale-free power spectrum that you transform scale-free metric perturbations or potential that you transform into density with a transfer function due to the Mezauer effect and so on. Mahmoud 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 Bashar. Oh, here it is. Yeah. المفروض يشتغل؟
بس ما اشتغلش على السكرين.
يشتغل على ايه؟ So this is a simulation I showed you in the first week, in the first lecture. Now maybe it's more understandable. This is the dark matter perturbation. Okay? So the dark matter perturbation, there's no pressure. Everything collapses really top hat. It expands in the beginning with the universe, then you're up top hat. And these are the scales. And this is like the direction, which is 1 plus A proportional to T2 or 3. So A is 1 over 1 plus Z. Okay? So the scale factor is the inverse, so 1 plus Z. So at scale factor 1, we are now as n equals 0. So this is the kind of thing you get. And it fits quite well the observations. Just dark matter with putting galaxies following the dark matter. Matter following light following matter. Okay, and you can get the same parameters as from the CMB. And there are some details. There's little acoustic oscillations that you can match with oscillations in the CMB. Sound waves, but this time in the power spectrum of the galaxy, but very small because it's dominated by dark matter this time, which you could also use as rulers and so on, and to constrain your history of evolution and things like that. There you go. Okay, now the problem, not the problem, but خلاص. أجاوب. ماشي. أجاوب. 5 minutes more, 10 minutes, hopefully. And then we have like 20. I hope we'll have 20 minutes. بعد كده. So these are big computer simulation, 100,000 cores. I mean, but usually this kind of simulation, this is old again. This is very old, this simulation, but I conveniently have it in all my slides. But the newer stuff, 10,000 cores is more or less enormous. 10,000 cores. We have a small system of about 400 here. That you can, because we're only using it for ourselves, we can do reasonably good stuff. Because, I mean, the bigger supercomputers, they have like groups of hundreds working on them, and you have to apply and so on. We don't apply, we just ask Mahmoud. So, okay, so the old picture of the formation of galaxies, here we come to galaxies finally. How do they form? They form inside these clumps and halos. So the standard pictures are by White and Rees and Fourier and Estasio and so on. The gas is shock heated to the Virule temperature, which is our fundamental equation of equilibrium here. The equilibrium mv squared, kinetic energy, which matches a potential energy. This is a rough order of magnitude approximation for a roughly spherical system, is connected to a temperature, to the gas, a thermal temperature, okay? Simply like the Boltzmann constant. NKT. Okay? So you assume that the gas falls inside the halo and it shocks. هيخبط في بعضه يسخن جدا. All the gravitational energy is being turned into thermal energy as it falls. It reaches the Virule temperature. Then it cools and starts to form stars. Devil in detail. Why do some things form stars very quickly and become elliptical galaxies? Why do some of them don't and become spiral galaxies? A very important thing is specific angular momentum here, how much you can spin up. So the halos have different angular momentums because of tidal forces between the different halos during these collapses, tidal gasomedia. Okay? So the angular momentum of the system determines to some extent why some things spin up like a ballerina spinning up and become a disk. Some don't spin up enough. They form stars in the middle. Cooling is very important, and heating also, feedback and things like that. I will get to that in a bit. Then in the standard model, you form small things first, as we saw, because the power spectrum is tilted to the small things first. Then they start merging and forming bigger things. That means you can't form big disks until late. Okay, this is it seems to be a prediction that is more or less well, well verified, but, even this last James Webb picture you saw at Redshift, which was what, Redshift 8 or 9 or something, had some spiral galaxies, which is very problematic for these models. Because the spiral galaxies during that time are supposed to be doing all the stuff not being here. Okay, so, but of course that needs a lot of statistics, but that's what people have been looking at. Up to now, it seems that the fraction of large disk galaxies increases with time, and up to a few years ago, at least when I heard the talk about that, it seems like it fits fairly okay the standard model, which is called the lambda CDM model. And you can see the mergers of galaxies. You can actually photograph them. You can see galaxies merging, two galaxies merging, they turn into an elliptical because they collide and things like that. Okay, but there are problems. Some of the problems, I worked quite a bit on that, and there's some extra slides if you want to know some solutions and ideas and these things. So, you put the halos and the dark matter and all this thing to fit the outer parts of galaxies. Because the rotation curve was going down, you wanted it to be going up. Well, the CDM has too much of this in the center, by far, usually. There is dispute on how much and how serious and so on, but I would think it's quite significant. And I think, at least for some galaxies, this is the consensus, that it's significant. So you have this is a rotation curve, so this is the mass squared, okay? So you square this to get the mass. Okay, so this is a significant difference. And the other factor of 2, this means you have a factor of enclosed mass by 4 or 5, almost an order of magnitude. Okay? So this is problematic. You may want to chase it out like I did or some other people did. You may want to choose other types of dark matter and so on. And then you have, this is because the cold dark matter is so cold, so it clusters quite very efficiently. And then you have too many small, there you go. Give to. Okay, and then you have too many small clumps and so on. This is a simulation of a Milky Way-like galaxy forming in the lambda CDM model, and this is the CDM. It makes, you only have in the Milky Way, they're increasing with bigger, better telescopes, you're finding smaller satellites all the time, but they're still in the order of a few dozens, and this is of the order of a few hundreds. Where did the small galaxies go? Where you have all these little clumps, because the thing, it doesn't have any pressure, the cold dark matter. So it forms really lots of clumps, maybe even down to solar system size, Earth mass. So where are all these things? We don't see them in galaxies. Now, there are a lot of solutions to that too, but that's another thing. And then there's the high redshift stuff. I'm sticking to the ultra deep field of Hubble, but there is the new stuff with James Webb, which will revolutionize this field completely. This is the picture I showed you in the first day. Now, as the way as it looks nice in some sense. This is from the ultra deep field. The new Hubble is not that different. I mean, the new James Webb up to now. This is from it looks nice, but devil in details. It looks nice in the sense there are many more smaller galaxies that appear to be merging, which is the prediction of the lambda CDM. Okay, that there will be many small things. But the lambda CDM doesn't predict big galaxies at high redshift. And this is a very conservative paper here. Some people have these observations going on here as of that. So, because our power spectrum was tilted towards smaller things. So at high redshift, then it was 6 or 7 here, or 5, and this is 7.5 or 7, 6.5. You shouldn't have really a lot of big galaxies. Now, This is the mass function. So these are big masses, and this is the number of galaxies per mass range per unit volume of your universe, and blah blah. Okay. So this is the number of massive galaxies. Take home thing is the number of massive galaxies is very big compared to what you expect. Not very big, but appears to be a bit big. Okay. Because general details. How do you really measure the mass of a galaxy at redshift 10? This is difficult. James Webb will be very powerful on that because these are mainly, up to now, ultraviolet luminosity functions, which are very difficult to convert to masses. This is rest frame ultraviolet coming to Hubble, and not Hubble, this is not Hubble, I think there's even Keck or something. But anyway, indivisible. Okay? So rest frame ultraviolet coming to Hubble or Keck or whatever, indivisible. James Webb will get rest frame infrared with much more power. Visible in infrared, so you can disentangle the mass functions much better. You decrease your error bars, do things. So if there are a lot of big galaxies, especially before like a few 100 million years or so, from the beginning of the expansion, then you're in serious trouble. Even small galaxies before 100 million years will be problematic. So this is a way to test this whole edifice from the creation and annihilation operators to العك بتاع الgastrophysics. عك is the mess of actually what it looks like to model this stuff. Horrifying stuff. The details of the ecology of the galaxies, which is more like ecological science than it is like it's more like global warming than it is like fundamental physics. The great thing about cosmology, it connects the fundamental physics to the ecology, and one day to the simulations, to a lot of nice math, to a lot of nice observations, to a lot of interesting physics, equilibrium, non-equilibrium. As Jerry Gilmore, who's an observational physicist, he said all of Landau-Lifshitz is there, the big 8 volumes, plus if you want to do early universe, much more actually. Okay? Or modified gravity and things, much more than numbers. Okay? So, plus experimental work that is extremely difficult and demanding, big data science, machine learning and artificial intelligence, all the nice stuff. So you have everything here. Okay? Particle accelerators, where is the bloody dark matter? Particle physics, so you get everything. So it's a really nice field that is on probably a verge of a big catastrophe, so it's nice to work on it, because you can't find dark matter. So here's what this looks like, conservation equation. This is a viscosity term, usually turbulent viscosity you're talking about. Friction, if you want to really simplify it, but turbulent, not usually the Reynolds number are very high, not usually viscosity in the sense of the CMB or streaming. It's not that. It's not due to shearing. It's due to turbulent, usually in the galaxy. Then you have energy feedback from supernova. You form stars, the stars explode. You don't know where does this energy go? Does it move the gas kinetically? Does it cool? Does the energy go outside? Do you form active galactic nuclei in the center, a black hole and jets? Do you what is the cooling? What is the heating rate? How do you transfer the energy? And then there's a lot of nice atomic and molecular physics here. Free bound transitions, molecular cooling, inverse Compton effects, which I will not talk about. Thermal instability, Rayleigh-Taylor, and convection, turbulence, and all sorts of really very complex stuff that is very difficult to model in this energy equation. This is called an energy equation, which we couple with a Navier-Stokes here, not an Euler anymore, this. And some things, however, can be understood quite heuristically. Small galaxies, maybe you don't see them not because the cold dark matter model is wrong, but because the potential of the cold dark matter is so small that you blow out all the gas and stars and they die. You form one generation or two of supernova and they blow out the gas and they die. You don't see that. Dead galaxies, dead galaxies. Then there's the too big to fail problem, but that's another story. It's connected to this cost core, the rotation curves I mentioned. You can't form big baryonic galaxies because هيبقى شيء 10 to the 12 solar masses مش هيبقوا في العمر الكون. Right? You can't form very massive galaxies because they will not cool. And if they don't cool, they will be like cluster where you find hot gas in dynamic equilibrium that is thermally supported. Not thermal equilibrium, dynamic equilibrium, thermally supported, which is near thermal equilibrium, but not exact. In the case of hot cluster gas. In gravity, you have to really take care of the difference between thermal and dynamic equilibrium, things like that. Really take care. But in hot cluster gas, it's reasonably well defined because it's really not self-gravitating, it's in the gravity of the halo. And it's supported by pressure, by thermal pressure. So before the gas doesn't have time to cool in a cluster, so it doesn't form stars and so on. So that's why clusters are not clusters of galaxies are clusters of galaxies. Huge galaxy. Maybe this is your question in another context. Why can't we form a star in a galaxy of 10 solar mass? Okay, so this is really it. I said there should be discussion. So, okay, before the discussion, if you do the direct determination of the Hubble constant like we did the first week, and through the equations that we did, these nice equations that we did, you get another problem of the lambda CDM model is that apparently when you determine things this way, the Hubble expansion rate is like 73, 74, whatever, while with the CMB and the other things like it, you determine it to be 68, and this is another problem of the CDM model. So the model is really nice, except that you only have 5% of it. You know what it is, but it works very well otherwise. And it does form galaxies, and in many ways is extremely successful, especially on a large scale. It remains to be seen if we need a revolutionary physics or it's all in the gastrophysics, which is a gastronomical disease. حاجة في المعدة يعني. It's like a disease that of all these complex physics that we don't understand. And maybe when you understand it, we have bigger computers and better formulas for that and better observations, maybe things will work out. Or there's a revolution in fundamental physics, at least of the same scale, maybe as 100 years ago, maybe, perhaps. So it's a very nice time, and there are a lot of instruments that I put last time, and this is like a fraction of the instruments coming up in the coming period. James Webb is already on, there's SK, that would be having maps of the universe at different times. And there's stuff, polarization of the CMB, did you mention that? About B modes and so on. Then, people are asking me, is James Webb the first thing we'll see in the universe? James Webb is like maximum 100 million years. This is like 10 to the minus 30 seconds. After, okay, so this is much further than James Webb. Okay? 100 million years, 10 to the minus 30 seconds. And on that positive note, I'll stop. Okay.
So I believe that those who will partly spoken about a theme used Hubble to that they discovered galaxies without dark matter.
Yeah.
How does it go with CDM?
It goes in different ways, and some people think that we did it. But actually, this kind of, there's a lot of disputation of the observations and so on. Okay? But assuming it is true, this is more in line actually with lambda CDM than with modified gravity. Because if it's modified gravity, there's no way that you wouldn't have modified gravity. It's a fundamental theory. But with lambda CDM, we can blow it out, and we can do, for example, we can blow out a lot of the dark matter in lambda CDM because we don't know the amount of feedback and how many stars are exploding and things like that. So, and when the stars explode, they do fluctuations, turbulence, like Niagara Falls. And this Niagara Falls, you can do it coupled to a Poisson equation, becomes a Niagara Falls in potential. And this potential heats up the dark matter, you can expand it a lot, you can blow out a very large fraction of it. So this is something I'm actually working with Mahmoud on, trying to figure something out. So it's possible. not easy to drive all of it. We're having trouble with the core. but in principle, in lambda CDM, it's not deadly. It's deadly for water. But the modified gravity people also have, to be fair to them, they also tell you, in MOND you have to take into account the interaction with another galaxy, and it's not linear, and so on, and all. And we don't know, but the problem is they don't know how to calculate it. So, in lambda CDM, it's better, I would think. The situation is better.
Also, like things like bullet cluster, you also can see like.
Yes, the shock wave. Yes, you can see the shock wave of the bullet. Something called the bullet cluster, where you have something, a shock wave, زي طيارة, like a supersonic plane, but you don't see the plane. So it appears to be a dark matter going through the gas, the hot cluster gas I was talking about. The hot cluster gas. The gas in the clusters didn't have time to cool because it's like a kettle that is very hot and 10 to the 12 solar masses. So the gas didn't have time to cool. So it's nearly homogeneous hot gas supported by thermal energy against gravity. So, and you have this piece of dark matter probably going through it. It does a shock wave, bow shock. Like a supersonic jet, and you can see that, and you can't see the galaxy. So this is fairly reasonable evidence. So we, first of all, are there questions on this? And then we could have a more general discussion. We still have like at least 15 minutes. في أسئلة عن ده الأول؟ أنا قلت أعمل لكم كل حاجة بقى من ده الكريسندو of the school. I'll throw everything, throw you everything, because you got used to being things thrown at you. So I decided that Now this is not meant to be. This is meant, like I said, to be a window shopping for getting an idea of what's on the market. What are things we think we know, and what are things we don't know. The reason we don't know them is because we think the things we think we know, we know them well. And that's what produces the gaps. But the gaps are not small, as I hope that could be seen. So this is the field, at least the part of the more empirical part. But like I said, it's connected to the more theoretical, all the way to 10 to the minus 30 seconds quantum fluctuations. So I think it's impressive that you can do that. But there are big failures, as with the Rayleigh genes was also impressive, and the calculation of the Planck spectrum, or the tail, Rayleigh genes tail of the Planck spectrum is also impressive. But because they could calculate it, and they could count the modes, and they could do the classical stuff, they found that you couldn't do it this way, and you needed h mu and so on. If they didn't calculate it classically probably and found this gap and this discrepancy, you wouldn't need. So maybe you are in something like that here, because we can calculate that precisely. Now I need complaints. I need somebody to complain. Hey. To tell me, for example, which... You have a complaint. Okay. You have a complaint? No. Okay. Fine. Okay, if there's no questions about that, then general comments about this thing. Obviously, some things were very hard. It was not meant to be a pedagogical thing. These things need a whole course, and also especially for the people from undergrads and so on. I know this could have been difficult, but what I mean, do you have any suggestions how could it be made easier? Too many, huh? لا ما نقوله يعني ايه اللي مثلا ايه اللي كان ممكن يعني تعمل احسن بطريقه. طبعا تبسيطه زياده عن كده هيبقى popular على الاقل في حاجات مثلا، يعني في حاجات معينه ما تقدرش يعني دي التوك دي لو بسطتها عن كده هيبقى popular science. يعني طبعا انا كنت ممكن اعملها 4-5 محاضرات وده الصح، وفي حاجات في الابندسز، لكن لو اتبسطت قوي مش هيبقى مش هتعرف، مش هيبقى واضح اصلا على الاقل كده طشاش الحاجات جايه منين، ونبص في الكتب ازاي. فالمفروض يبقى في شويه تفاصيل، ما ينفعش يبقى كل يعني هل ده كان مفيد التفاصيل ولا المفيد اكتر العام؟ في ايه المفيد لو في حاجه مفيده؟ طيب وليد انت مثلا، وليد هنتكلم مع دكتور وليد عشان دكتور وليد مش هيتكسف.
لا هم اللي يقولوا.
بس عظيم. So sometimes a good introduction of the motivation for this, motivation, why do we go through all this heartache? Okay. وكان المفروض يبقى مكتوب طاقة محمد هاني عن measurement theory of the mechanics. بس هو عيب.
الشغل اللي هو بتاع فلاديمير برجينسكي اللي هو الناس measurement theory في الشغل التكنولوجيز بيعملوا gravitational waves دي مثلا developments مهمة جدا فلاديمير برجينسكي الناس اللي هم بتعمل الشغل بتاع gravitational waves والبريسيشن وبتعمل measurements التشابه اصلا كده.
Which gravitational wave?
وفي حاجة مهمة قوي ان احنا نفرق يعني it's very important to distinguish between mainstream fields or mainstream subjects, okay, or other directions in research which don't really know if it's going to be fruitful on the long run or not. Measurements reliable ولا للإيرلي liable quantum effect? I don't know how.
Why it's possible, but I don't think so. Because LIGO is really a very classical regime. The things they are measuring are very classical. So, and the way they calculate is just too hard.
It's easy without.
You mean the quantum effects are not in the gravitation?